little bit. So today we're continuing 16.2 because we obviously did not finish it on Friday. So that's just a little talk. So we had some fun on Friday learning how to parameterize, reviewing how to write an equation of a line in parametric form. Then we learned the main formula for line integrals, which gives you two things, right? But they actually give you more than these two things. But they give you the area of a curtain hanging down from the curve, and they give you density or mass of a wire, if the function represents density. They also give you more stuff too. So anyway, so these are your formulas, 2D and 3D. You should have all these written down. We did a little practice. All right, and then we did some more practice and had some more fun, again, writing the curves in parametric form. Yay, parametric form, right? Okay. All right. So we did not do this one. So let's go ahead and do this just to make sure we are comfortable with line integrals. So remember the mass of a spring, that's just the mass of the curve, the wire. So with the given density functions, that's your density function, they've given you the path that the spring follows already in parametric form, so you don't have to convert, it's already given to you. So your goal then is to see if you can, first of all, you're going to have to rewrite your density function, so in terms of t, right? And then see if you can look up or remember the formula for line integrals and get this set up properly. And we'll check our setups in a minute first, and then we'll make sure that we can evaluate. I know you can evaluate. The setup's the most important part. So take a minute, talk to each other. Good. There could be a mistake in my setup. Did you guys get a different setup? Yeah. Okay. So my r prime is 1 over root 2 times, so it'd be, vector, there we go. So it'd be negative sine t, comma, cosine t, comma 1. Right? Okay, so our mass is the integral. They gave us the limit, 0 to 6 pi of, so it was 1, what was it, 1 plus z? And z was t over 2, right? T over root 2. Yeah. Z was t over root 2. So 1 plus t over root 2 times, and then it's the square root of, so this would be sine squared over 2. Oh, yeah, it is root 2. Yeah. Sine squared t over 2 plus cosine squared t over 2 plus 1 over 2. And so I just pulled all the 2's out and put it as a root 2 out front. Okay. But that's your setup. Okay. And then sine squared plus cosine squared, you know, is 1, right? So this whole thing is just equal to 1 plus 1 or 2 over 2 or just 1, right? So you just end up with this whole thing just being 1. So you end up with just this, and doing the antiderivative of this, dt. Because your whole root equals 1. Any questions? Zach, how you doing? Good? Yep, that darn root 2. Okay. Good. Any other questions? Sophie, you good? Okay. Dorsa, are you okay? Do you see why the stuff in the root is 1? Can you simplify it? Do you? Okay, so this whole thing just becomes 1. So really you're just antidifferentiating 1 plus t over root 2, right? The antiderivative of 1 is t. The antiderivative of t is 1/2 t squared, so you get 1 over 2 root 2 t squared. me. We talked about this already. I showed you the cute little thing with the ball moving on the wire or whatever, the bead on the wire going through a vector field. So when you're doing a special line integral of a vector field is almost always done in the context of work. I don't know if I've ever seen a problem that wasn't in the context of work. So at the bottom of this slide is where you finally get the formula for line integral of a vector field, which is really just f, it's dot dr, but I always write fdr. It's really f dot dr. I like FDR just because I like FDR. So I've been watching a lot of podcasts about former presidents or listening to them on my drive lately. So anyway, so dr is really, you can, if you have this parametrically defined in terms of t, it's really f, think of dr as r prime. Think of it as derivative of r. So it's really the dot product of f and r prime dt if everything's defined in terms of t. Think of it as f dot r prime. So this is a work done of an object on an object moving along path r of t through vector field f. So this integral gives you the work done on an object moving along the path r of t through a vector field f. Which I think this is already in your notes. But if it's not, it's okay. Did we do this one yet? No? This is where we left off? Okay, good. All right, so evaluate f dot dr if f equals the function xy comma y and r t is the function 4 cosine t, 4 sine t. So r has already been defined for you parametrically. And the first thing that you have to do is rewrite f in terms of t. So if you have, if the first component of f is x times y, bless you, then the first component becomes 4 cosine t times 4 sine t, x times y. Think of it like your r of t, that's your x, that's your y, and then you use that to rewrite your f in terms of t. Good. All right, so f dot dr, there's my f dot dr, but first you got to rewrite f. So there's my rewrite. Check your rewrite, make sure it matches. Yes? Yeah? Any questions on the rewrite? That's just f, and that's r prime. Remember, it's f dot dr, it's f dot r prime, right? So this isn't r, this is r prime. This is f, this is r prime. Any questions on setup? Now you got to find the dot product. Do you guys remember how to do a dot product? Okay, go ahead and do the dot product. See what happens. Is this what? I don't remember. So let's see. For multiply, you get negative 64 sine squared cosine plus 16 sine cosine. I would factor some stuff out. Let's see. Bless you. Oh, I would do a U sub on this. I would let U be sine. Sine t dt. So you end up with just negative 64 u squared plus 16 u du, right? And then you just back up into it. So anyway, and you change your limits. And I got negative 40 over 3. How did you do? That's what you got? Good. Okay. All right, any questions? All right, there's more. All right, find the work done by the force field F of x, y, z on a particle as it moves along the helix given by r of t equals cosine t plus sine t. So it's the vector, cosine t, sine t, t. Very similar to the last problem, except they didn't give you the starting and ending t values. They just gave you starting and ending points. So you have to figure out your starting and ending t values for your integral, which actually is really easy because remember, these are points on r of t. So you just have to ask yourself what t value gives you this point and what t value gives you this point. Starting and ending t values first. So what angle has a cosine of 1? 0, right? And then you just kind of check, does sine of 0 equal 0? Yes. Does 0 equal 0? Yes. You could really just look at the t, right? And be done. So if t is 0, so we're going from t equals 0 to t equals, and then this one's really darn easy then, 3 pi, right? Okay. All right, so we got that. All right, our f of t, rewriting f in terms of t. So, whoops, this should be a vector. This is terrible. I have so many mistakes in here. Okay. All right, so there's my, what do I have? Where did my t's go? 1/2 x, negative 1/2 y, and then, oh, there's no z to plug into. It's just 1/4. Yeah, no, it's right. It's right. Okay. All right, my r prime, negative sign, again, should be a vector. I don't know why I didn't write these as vectors. All right, there's my f, there's my r prime, and then we do f dot r prime. Again, pretend those are vectors, and you end up with 1/2 sine cosine minus 1/2 sine cosine plus 1/4, and you end up with just the integral 1/4, which is nice, right? So you anti-differentiate, you get 1/4 t from 0 to 3 pi, and you end up with 3/4 pi. What's the matter? Did your cosine sines cancel out? You know why? So I almost went down that road of changing this to 1/4 t, but there's no z here. It's just a constant. So it just has to stay a constant. Yeah, that's tricky. Good. Any other questions? Vikram, you good? Okay. Moving forward. All right. Line integrals with respect to x and y. So moving away from parametric form. So suppose we have a function that's defined. You're going to see this kind of presentation a lot. And there's a way that this presentation is derived from the other presentation. And I have it somewhere in my Smartboard notes, but it's not in this lesson. I think it might be in the next lesson, where I show you how you move from the old arc length method into this method with a function, some function dx plus some function dy. So anyway, so suppose you think of this as kind of like your f, and here's your r of t, and we're going on the interval from 0 to 2 pi. So if we want to stay in terms of x and y, remember that this is your x and this is your y, right? Now you could go ahead and do your replacement and figure it out. That's me just doing it. Shoot. Here, where did I actually put the things? All right, so x, I must have not written them. X equals 3 cosine t. So if we, and y, I'm going to do the y. Y equals 3 sine t. I'm going to do it the dy dx. So dy equals 3 cosine t dx. And your dx, so my dx equals negative 3 sine t dt. I had this all worked out in this nice way where I could show you how everything like cleans up and cancels. So anyway, so my x is 3 cosine t. My dx is negative 3 sine t dt. So I'm taking that right here and I'm plugging that in for my dx, and then my dy, that's just converted, is my 3 cosine t dx, but there's a simple way why it's not it's dt, there we go. Ugh. That's what was throwing me off, was why did I have that dx there? Okay, negative 3, or 3 cosine t dt. So then I take this, and I replace that in for my dy. So the nice thing about this is you don't have to do the whole arc length thing. You don't have to do the r prime square root of x prime squared plus y prime squared or anything like that. You can go ahead and just find your dx, find your dy, and then just start replacing everything with your x, your y, your dx, and your dy. So it's kind of a nice presentation for line integrals where you don't have to do it with respect to arc length. And believe it or not, it still works. There's a way of deriving this method, but I think I put it in my fundamental theorem of line integrals notes. So I think you're going to see that in the next lesson, not in this one. Okay, so anyway, so let me walk you through it a little bit better so it's not all messy. So the first thing we know is we know our t's are going from 0 to 2 pi. So we have y cubed. Y is 3 sine t. So y cubed would be 27 sine cubed t. dx, so you write your x function and find your dx. And it'd be with respect to t. And then your x is 3 cosine t, so x cubed is 27 cosine cubed, plus 3 times your x times your y squared gives you 81 cosine sine squared, and then times dy, and dy would be, if y is 3 sine t, dy is 3 cosine t dt. And then you just pull the dt's out and put them at the end. So I kind of like the problems that are presented this way. For some reason, doing the arc length kind of bugs me. So this one, to me, it's just kind of a plug. It's more plug and chug. Does that make sense? I did it kind of haphazardly. Okay, so if we clean this up, I don't want to sit here and evaluate integrals all day. So if we clean this up, we end up with this. We have sine to the fourth, negative 81 sine to the fourth plus 81 cosine to the fourth, plus 243 sine squared cosine squared. This is almost yelling factor. Does this make you think factor? No? Not at all? No. Cosine squared. I did. I factored. So these two terms, 81 cosine to the fourth t minus 81 sine to the fourth t, I rewrote them, just reversed them, and saw a difference of squares. And said, hey, look at that. It factors. So I pulled the 81. You can pull an 81 out of every single term. And so I factored that into cosine squared plus sine squared times cosine squared minus sine squared. And then this guy, so guys remember sine 2t equals 2 sine t cosine t?
What? Huh?
Double angle identity for sine?
Yeah, no. We're not doing this.
So
Is not the move for Monday.
So anyway, so I just moved the 2 over and did it twice and made it a 3/4 sine squared. This is kind of some work. There's nothing this insane. Like I promise you, there's nothing this crazy on your test. So anyway, this part we know is 1, right? And then you just left with cosine squared minus sine squared plus 3/4 sine squared, right? And then you can combine the sine squareds. So you end up with just cosine squared minus 1/4 sine squared. And you either do a power reduction. Yeah, you do a power reduction. Cosine squared minus sine squared is cosine 2t, right? Double angle for cosine. So, fun with identities. Yeah. Okay, so the main thing for this problem, I knew this was going to be a bear. The main thing for this problem is just the setup. Can you do the setup? I don't ask you, I know it's been a long time since I gave this test, but I know I don't ask you anything with like a whole bunch of trig identities and trying to spot factoring on separate terms and all that kind of stuff. There's nothing that crazy. Ian, could you set it up? That's all I'm worried about right now. You got it? I'm not worried. Good. All right. Are there any questions just on the setup? Yeah, right. I don't think so. All right. Now, okay. So, if everything, including your R of t, is presented in terms of x and y, you don't have to use t. Okay? Now, here's why. So again, this is kind of similar where we're just going to do some plugging and chugging. So our y is 4x minus x squared, right? So we can replace the y with a 4x minus x squared. Dx can just stay dx. X squared can just stay x squared. All we need is a dy. So dy, well, what's that the same as? That's 4 minus 2x dx. So you just replace the dy with a 4 minus 2x dx and the y with a 4x minus x squared. And now you have a big integral just in terms of x. And then, we're going from this point to this point. If we're integrating completely in terms of x, what would our x's be from and to? From 4 to 1. Did you what? you could flip, if you want to make it negative and flip them to make it go low to high, that would be nice. There's me just writing all this up. Do you all understand how we replaced the y and how we replaced the dy? Everyone comfortable? Okay. All right. Do you want to do this one? It's really easy. Yeah. Okay. I know you can do it. All right. You know you can do it, right? You just combine like terms, you get a polynomial, life is easy, and the answer is 69 halves. So if you're given an F, a vector field that's written in this format, and you can think of this, so our old book always used M, N, and P for M dx, N dy, and P dz. Our new book uses P, Q, and R for the same thing. So P dx plus Q dy plus R dz, if I remember right. When you're given a function in this format with the dx and the dy and in 3 dimensions with a dz, then if you're given your R of t in terms of t, then you just do some replacing. Replace the x's with what x is, replace the y with what y is, and then solve for dx, solve for dy, and replace the dx and the dy, and then everything's in terms of t. But if you're given an R of t that's just in terms of x and y, you never even have to go to t's. You just replace what you need to and keep everything in terms of x. All right, that is it for 16. Time runs out. All right, so for the first one, evaluate the line integral. You have f equals 2x minus y, and r of t equals this. And again, this one it's just an arc length method, right? So you would find your r prime and then square root of x prime squared plus y prime squared. Convert your f in terms of t's from 1 to 3. Value of the integral. All right. Find the work done by this force field F on a particle that moves along this curve from this point to this point. So you'd have to find your t values, the from and to for t, which is not too hard. And then it's f dot r prime, right? It's just the integral of f dot r prime. And then for the last one, find the mass of a wire follows along this curve whose density is just x over the interval from 0 to 2. Use your R of t to rewrite the density in terms of t, so the density would just be t. And then remember, it's just the line integral of the density function. So you'd have t square root of x prime squared plus y prime squared from 0 to 2. All right, so 3 kind of types of line integrals, all slightly different, but all similar in ways. Okay. So today we're going to talk about conservative vector. Oh, I didn't change the thing. Oh, I thought I had updated all my lessons and gotten them all with the right things. There we go. Conservative vector fields and independence of path. So the fundamental theorem of line integrals is all dependent on your vector field being conservative. All right, are we ready? We'll just start. All right, okay. So this could be a good whiteboard problem. I think we're gonna do this on whiteboard. Okay, wait. Okay, so find the work done by the force field. So that's your F function. And then this is your R. This is one problem. This is another problem. This is another problem. Think of them as 3 different paths traveling through that force field. So do the f dot dr, right? So you're going to do line integral since we're doing work. We're going to do f dot dr where r equals x, and then where, oh, that's kind of weird, x equals y squared, and then y equals x cubed. So you're going to have to convert these to parametric. Yeah, you're going to have to convert them to parametric. So convert these to parametric form, and then see if you can write setups, at least setups for each of these integrals. Some of them should be pretty simple to evaluate if you want to start evaluating. But see if you can get these converted to parametric form, find your correct t's, and write your setups of your integrals. 3 different integrals, f dot dr. Same vector field, 3 different routes. Same starting point, same ending point, 3 different roads that we traveled on, and yet the work was the same no matter which road we traveled down. Now, this is not a proof of anything, but it's evidence of something. So is there a conjecture that you might be able to make based on what happened here? Any ideas about the work done by a particle traveling through a vector field? Yes, Tajesh?
The work to move the particle along any, or I don't know if I'm right, but the work required to move that particle along a certain path, whatever it may be, if it's the same distance, should be the same.
What if the path is a different distance, but you get to the same point at the end?
And it's still the same?
It's still the same. As long as the vector field is conservative. So what ends up happening, it really doesn't prove anything. It's just evidence. But it is true that the work done to get from point A to point B through a vector field is exactly the same no matter how you get there. You could spin around 26 times, land at the same point, and you're still going to have the same work done as if you went straight there in a line. So that's the guiding principle for the fundamental theorem of line integrals. So here's what don't worry, you're going to love this, okay? This is to make life easier. Okay, so the fundamental theorem of line integrals says that if C is your path, remember. If C is a piecewise smooth curve lying in an open region R, given by R of t equals x of t, y of t from A to B, and F is some conservative vector field also in that same region, and your components of your vector field are continuous. So there's a lot of ifs. Yes, Sophie?
Does this mean that if you have to find the work from with a super crazy path, you can just find the points it goes to and use x equals y for the path?
For this, yes. I don't know about in life. But yeah. For this, yes. So here's what happens. So we know that the line integral over C of f dot dr calculates the work done along path R through vector field F. So what this is saying is if this is true, if big F is a conservative vector field and your path, like C, is a piecewise smooth curve, then there's 2 things to actually gather. One is, if you have to do a line integral, if you can't do fundamental theorem of line integrals, you can pick any path you want, right? You don't have to follow along some crazy path with a bunch of trig. You could just do a line and life is good, right? However, there's another little fun thing about this. So this is big F. This is the gradient of F. So what it's saying is that big F is, how do I say this? Little f would be the potential function for big F. So I don't know how to say it. The derivative of little f would be big F. So if you can find the potential function for big F, it's just the potential at point B minus the potential at point A. So you end up getting something that's really similar to a traditional integral. If you have a definite integral, I don't remember I have in the notes, but if you have a definite integral, just old-fashioned, like some function f of dx from a to b. Remember that this is little f of b minus little f of a, where f is the integral, the antiderivative of big F, right? So you just do the antiderivative, plug in the b minus plug in the a. It's the exact same thing here, just in vector field world. So what they're saying is that work done, that f dot dr is really just if, and there's a lot of ifs, if the functions are continuous within your vector field, if the vector field is conservative, and if the path is a piecewise smooth curve, then you can find your potential function for your vector field, plug in the b minus plug in the a, and you'd get the exact same integral. Okay. All right, so let's look at the notes. Oh, that's me just saying, hey, look, it's really similar to the fundamental theorem of calculus, just with line integrals, right? Okay, so almost exactly the same. Hey, there's another.
It's almost like.
I know, I'm sorry. There's another note. If you had to move this into 3 dimensions, it's exactly the same thing. So this is your potential function. Instead of just an x and a y evaluated at b, it's an x, a y, and a z minus your potential function x, y, z at a. So same kind of thing, just expanded to 3 dimensions. All right, I don't know if we have time to do one more example before the bell rings. Did everyone get that written down? Let's see if we can just do a setup. All right, so suppose C. Yep. Sit, just do it on paper. All right, so suppose C is a piecewise smooth curve from point -1,4 to point 1,2. That's your vector field. We're going to evaluate the work done on the point moving along curve R through vector field F. And notice, oh, I did a quick check here. I'm showing you that the vector field is conservative. So all you have to do is find your potential function, and then you have to find your points to plug in. Actually, you're given. You can do it in terms of x and y. So find the potential function, and then see if you can evaluate using the fundamental theorem of line integrals. Or at least set it up. Hey. Okay.
What's A and B? So is A starting if you yeah.
Whatever. All right. Thank you for telling me that. All right.
Thank you.
All right.
We are actually.
Okay. So potential function. Did you all get x squared y minus 1/2 y squared?
Yes.
Yes? Okay. Plug in your points. You can keep them in terms of x and y, and you just combine. You just plug in the last point minus plug in the first point. You don't have to find your t's, and you just plug them in. It's really easy. It's not bad, right? We will continue this tomorrow. You're going to love it. Honestly, like fundamental theorem of line integrals is really fun.